Sarah, Tiago, and Sergey, and we are the Roomba Calligraphy team. And as our name suggests, we use the Roomba to do. And as our name suggests, we use the Roomba to produce a non-trivial drawing. More specifically, we wanted to use the iRobot Create platform. Oh, go back to. It's okay. To do a calligraphic drawing of our school logo. So on the next slide, we've created a list of 10 items that we thought were the most important, and these can be compiled into 3 main components. On the next slide, we have the Roomba, which is our writing device, and then the OptiTrack, which is our localization system. From the OptiTrack system, we get the position and orientation of our robot, and that is sent over Ethernet to our workstation. In this workstation, we're running a controller that uses model predictive control, and it takes the inputs from the OptiTrack system and sends a wheel speed trajectory over to the robot. And then this process keeps iterating up until our writing is done. So the hardware that we used to accomplish this was the Roomba that we've used in lab, which has the SB Rio that we use for the low-level control and a Ethernet adapter that we use to have Wi-Fi communication with our robot. To mount the marker onto the robot, we just use like metal beams that are similar to that from an erector set. With the rubber band to make sure that the pen would stay on the ground and that there's also some flexibility when you go over bumps. And we also used masking tape on top of the metal just to make sure that a lot of the reflective surfaces were covered and that only these markers were shown. And these markers were important because they were part of the OptiTrack localization system, and that's what the motion capture camera used. It would emit infrared light and then look for reflective objects in the space that the cameras could see. And then with the software, so the software that we used for this project was the Wind River Workbench to program the VxWorks system that ran on the SB Rio. The OptiTrack tracking tool system, which used the localization hardware to get the position and orientation of our robot. We used Blom, which was a toolbox that runs on top of MATLAB and Simulink, and that's what we used to run our model predictive controller. And we also use MATLAB to interface the Roomba with the localization and our workstation, as well as to create a GUI so that we could do this a little bit cleaner. Okay, and then Sarah's going to talk next.
So the main strategy for our project involves something called model predictive control. So to give you the basic idea of what model predictive control is, can kind of be seen in this graph right here. So the idea is that you formulate an optimization problem to achieve some goal. For us, it's tracking a trajectory. So in this example, we want to sort of track, some sort of trajectory like that. And what happens is you formulate an optimization problem for a horizon. In this example, it's of length p, so that's your time horizon, and it calculates all the inputs you're going to send to your controller or your low-level controller to implement that action and to achieve your desired output. And what happens is that this predicts gives you a set of inputs over time p, and then at some later time, I think that says s, you redo the same optimization problem. So that way you're getting your feedback into the controller. So at every time step that you re-optimize, you're getting your position feedback and you're recalculating. Okay, we didn't quite make it here, so let's re-optimize for our particular trajectory. So our setup looks like this. You can even see it right on the ground in front of us. Basically what we had to do for our model predictive controller is we had to come up with our dynamic model for the robot. And basically that just requires X and Y position in a plane as well as its orientation, which we call theta. So as you can see, we have our coordinate system set up, and then what we did is we developed our dynamic equation or dynamic model, which we originally formulated, with respect to time as is traditionally seen. However, what we wanted to do is we parameterized it according to arc length of our trajectory, and this allowed us to play with the speed of the robot and have it go as fast as we could possibly make it go, if we wanted to, for example. So the two inputs to the system, as I'm sure you're familiar with from class, is the two wheel speeds, and those give us our outputs of position. And then we have our transformation over to our pen position as well. So this is the actual format of our model predictive controller. This is our optimization problem. It's basically, this is called a quadratic cost. Our horizon is of length n, so that's the amount of time you're optimizing over. And then our trajectory that we're tracking, we decided to use both a trajectory for the robot's center position as well as the position of the pen. And our arc length is s, so that's how we parameterized our system. And so basically, you know, we have our quadratic cost trying to track our position, and then we also have a minus cost on the s dot, so that just means go fast, you know, and we have a weighting cost that is associated with s dot because we can kind of play with how much speed we want versus how well we want to actually track the trajectory. And then the nice thing about model predictive control is that it directly addresses constraints. So the way we do that is, you know, in your optimization problem, you have your quadratic cost, and then we have we have linear constraints, in linear inequalities, and, well, not quite linear. And so those, constraints include our wheel velocity limits and our acceleration limits, because we want to make sure that the robot does not slip, because obviously if our robot slips, that's going to be very critical for the position of our writing. And then we had several parameters to tune it by, which you can see in further depth if you look into our report later. I think next. Oh, and just to sum up the model predictive controller, what we did was we formulated that all out, the optimization problem, and we implemented it in something called BLOM, which is the Berkeley Library for Optimization Modeling, which is, if you're familiar with Simulink, Simulink is a graphical control toolkit, and this is an optimization graphical library that is used for MPC. It's an extension of Simulink. Sari actually has worked on this himself. And so I'll hand this off to Thiago so he can tell you a little bit about the software infrastructure of our project.
So this is how mainly the software that's running on Roomba works. So, oh, thank you. So he's able to receive commands from the workstation that's being sent by MATLAB. So MATLAB is able to send a trajectory that the Roomba should do, the start and stop commands, and the synchronization timestamps. It also has we have two levels of controlling. One level is done by the op track, and the other level is low level, which is running on Roomba, which use a PI controller, so we can make sure that we are doing the right trajectory. And we also use semaphores for synchronization between the various blocks we have on the software. I will explain that. So here is a block diagram of our software. So basically it has three main blocks. We have our main function that's able to that's do the trajectory that it receives through the communication block, and the ISR that increments a clock every 50 milliseconds. And these two blocks work in a producer-consumer model. So this one releases a semaphore, and this one acquires the same semaphore. So then we keep them synchronized. You can go. This is how our GUI looks like. So we have our drawing right here, what actually we want to draw, and the several trajectories that the solver does, right? Here are the wheel speeds over the time. And we have also the delay from the op-track localization system, because it takes some time to localize where the robot is and to send us the command. Go next. No, we have. And this is how we set the trajectory. So we have our target drawing for call, and we use the input from MATLAB to set the points of the trajectory here. And these coordinates are sent to MATLAB so we can do our trajectory.
Hi. Okay, the project is essentially a closed loop control project, and timing it's maybe the most important issue in all closed loop control system. So I start talking about timing, and then I showed the main issues and challenges that we encountered as project. If we begin our loop in sampling of the Roomba image in OptiTrack, there is some unknown delay until the position is available to external user. We measure this delay by commanding a robot to move in specific time and measuring when OptiTrack is reporting actually that it moved. In addition, we need to transfer this information to the workstation. So there's another delay. We measure it by installing NCP on both computers, and then we can reliably estimate the delay by comparing the time take of the messages. In addition, when the message is received, we need to recalculate the trajectory. It's a significant time. So, but we measure it directly, and the main delay of the system is the delay to send the command to Roomba by Wi-Fi. This delay is known, but it may vary very high. I'll talk later about it. And so when the new trajectory is received in Roomba, we need to maintain that the first point of this trajectory will be in the future. So we need that the predicted position will be more than sum of all delays. So in order to accommodate for this delay, we need to predict the Roomba position based on the initial, based on OptiTrack measurements. And this is the required prediction. Unfortunately, this value is not always greater than 0 because this has very large variation. Okay, this slide summarized most of problems and challenges we encountered in this problem. I'll start from the main problem and talk about all other problems. So the main issue we have with this project is the delay in sending Wi-Fi messages from MPC workstation to Roomba. This delay may go anywhere from 30 to 3,000 milliseconds. Yeah. And unfortunately, we never found a complete solution to this issue. We managed to mitigate its effect, but it's not a solution. So one of the solutions, we're transmitting a long trajectory parts that are long enough, more than the maximum delay we see on this link. We can filter time synchronization messages, not to screw up everything. And if we know that we received trajectory that was late by a significant amount of time, we have in Roomba an algorithm that is comparing how much commands he missed and trying to compensate what he missed. But it's only partial solution. We tried a dedicated Wi-Fi router to install in the lab. It helps, but here actually, according to the security issues, somebody hacked into this router last week, and currently it's not working. Yeah. Okay. Now about the good stuff. One issue that the clock of Roomba is not very accurate, so we continuously synchronize the Roomba clock and workstation clock to keep everything in sync. In addition, what Iago has mentioned, the controller, the built-in low-level speed controller of wheels of Roomba is not very accurate. He has a low bandwidth and high arrow, so we implemented additional higher level PI controller that closed the loop on accumulated paths to make sure that each wheel did exactly the path length it's supposed to. It greatly improved the open loop performance of Roomba. A very important issue, if you try accelerate too much, the wheel is sleeping, and it's almost impossible to predict the sleeping ratio and the dynamics of Roomba in this case. So we limit the wheel acceleration in our MPC problem, and then we solve this problem. Another issue that sometimes we have seen that OptiTrack lose track on Roomba without no clear reason. Our conjecture was that it was a reflection of metal parts, so we used a reflective coating on Roomba. In addition, after all this, sometimes we see huge out-of-blue errors in tracking that are caused by unclear behavior OptiTrack. So we just, in our software, we can filter out very unexpected position updates. Another issue I mentioned that OptiTrack unfortunately doesn't have interface to report exactly what was the sampling time of the picture, but we measure it experimentally by commanding the Roomba to move, and then we know exactly when the command was given to Roomba, and then we can see when OptiTrack actually reported it, then we know the real delay. And a delay from OptiTrack to MPC workstation, we installed NCP on both places, and then we know exactly how long the message took to arrive, and then we can compensate for this delay by propagation. Sometimes the Roomba is lost in OptiTrack because it may go out of field of view or for some other reason. So we have a dead reckoning algorithm in Roomba. In our workstation. The trajectory computation itself is not a trivial one, like you will see. I hope so. The trajectory is not easy one, so we need to. And it takes significant time to solve. We use the state-of-the-art IPOP nonlinear optimization solver. It's probably the best solver currently available on the market. It's free for academic use, so we make use of it. So by using this combination of BLOM and IPOP, this is very high performance combination, we can solve the trajectory in less than 0.3 seconds. That's fast enough. And this, I mentioned that we use a predicted position of Roomba to compensate of all delays in the system. Done.
All right, so we're about to go to our demo, but first, we just want to show you the open loop controller. So the open loop controller, the open loop controller we ran before interfacing OptiTrack with it. So what we did was we ran our model predictive controller just with our initial guess for our position, and just ran all the inputs without any feedback at all. And so the open loop controller can kind of show you why we really do need the camera. So Brandon, if you could go back 2 slides to open loop and press play. There you go. So this is our open loop control, and you'll see that it doesn't quite make the image we want. So it starts off pretty good. You can see, the beginning of the C. Give it a moment. And then now you see it's starting to get off track. So it should be writing the A right now, but it's very close to the C. And so, you can see that no feedback is a bad idea if you want to be precise in your calligraphic writing. Okay. And the L is going to go way above the rest of the writing. So you can see it's supposed to be flat with this image, and it's completely not. So obviously open loop control kind of works, which is nice, but closed loop is we hope to show you closed loop is much better. And that's supposed to be the underline, and it's going off to the side. So it's pretty funny. Or you can pause it. And then can you skip to the end? And so before we run our demo, we hope to show you a successful drawing of a calligraphic image with our setup. And you'll see that the precision is not quite as high as we would like, but that's something that can be done in future work and could be accommodated by a more reliable wireless system. But we'd like to acknowledge the following people: Linda, because she helped us a lot with our wireless communication; Dorsa for helping us with the OptiTrack; Zach and Winthrop just for general help with hardware and that sort of thing; and our mentor Igor. Okay, now we'll show you the demo. We have to run the OptiTrack on this computer, so I'm just going to get over here and make sure that's working.
our GUI updates in the back if you can't see here.
It's off? Oh, yeah, I was in the front of the camera. So that's the workstation in the back that Sergey's sitting at, that where MATLAB is doing its computations. And in the front, we have OptiTrack. So the hardware is going to be running here, but you can also see the trajectory being plotted on the workstation too, if you can't see the actual demo. Can we actually move this and turn this off? Because I feel like this is going to interfere. Ooh. Oh, you started? Oh. Okay. Okay, so it should be starting soon. And there you go. That was actually good. All right, it's done. That's it. That's definitely not the best one we've ever seen.
Experiences high delay when the L goes in A, so yeah. We experiences higher than usual delay on A, so we may try another one. It probably will be better, yeah. Do it, do it, do it.
How did you get it to network so fast?
Sorry?
How did you get it to network so fast?
Hold on. Let me just get over here. I want to watch again. Okay, we're ready for take two. That must have been a loud delay there, too. All right, done. Yay. Okay. Are there any questions for us, I suppose?
So how easy or hard would it be to just input like a different word if you drew it out and then draw that?
It should be fairly easy. I mean, we have the G input program, and you just have to go through and click a bunch of points and then say, draw that trajectory. We just particularly like this trajectory because it says Cal.